All right, welcome back. This is the sixth lecture in this course, Bayesian Data Analysis for Behavioral Sciences. What we were doing so far was understanding probability and random variables, which would become very useful in understanding Bayesian modeling. So far we have discussed what are the three axioms of probability and how they determine what kind of probability assigner functions you can have and what is the role of these probability assigner functions in making a statistical inference, right. So the topic for today's lecture is that what are the some of the common examples of discrete and continuous random variables, right. So we are going to discuss some example random variables which are very useful. You can also call them probability distributions because eventually that's what we are going to talk about. We are going to talk about different types of probability assigner functions. Okay. Now, before going into this, I will just quickly um, walk you through what we have covered so far. So, we started with a very fundamental assumption that whatever data or observations you are seeing in your experiment comes from a true generative process, right. So, there is some true underlying generative process that is generating the data that you are seeing in your experiment. But the problem is you cannot directly know what is this true generative process. This is hidden from you. For example, this could be some cognitive process in the human mind. So, only thing that you can do is that you do an experiment, collect some data and use that data to infer the properties of this true generative process. Okay. But how do we do this? Well, in order to infer what is the true generative process, you need to make some assumptions about the true generative process. So, what kind of assumptions we make? So, we discussed that what we assume is that we assume there is a probability assigner function f, okay, with some parameter theta. So, theta is the parameter of this probability assigner function. Now, f could be of any form. We saw one of the examples in the previous lecture. For example, we saw this example, f of theta being n c x theta to the power x 1 minus theta to the power n minus x. Okay. So, now this is a function of theta. Right? So, theta is a parameter. This was, by the way, example for coin toss experiment, where x is the number of heads you would obtain in a coin toss, n is the number of times you toss a coin. Okay. Number of times you toss a coin, x is the number of heads you would obtain when you toss a coin n times, and theta is the underlying probability of obtaining a heads. So, for example, if a coin is fair, then theta could be 0.5. So, we call it a parameter because value of theta would determine what kind of output you would get or what kind of probabilities this function will assign to each number of heads that you would obtain in this coin toss experiment. Okay. So, coming back to this. So, whenever we are doing an experiment, okay, we assume that there is some true generative process, but we cannot directly know what is this true generative process. Okay. So, the only way we can do this is that using experimental data or observations, we try to infer the properties of this true generative process. But how do we do this? We do this by making an assumption that the true generative process is some probability assigner function, let us say f of theta. So, this is our assumption about the generative process, that there is a probability assigner function f of theta which assigns probabilities real values to events in your event space. These are called probability values. Because you are doing an experiment, it would have an event space, it would have events. So, this function f of theta assigns probabilities or probability values to the events in your event space. But this probability assignment must be constrained by three axioms of probability. Okay. So, we also discussed three axioms of probability. Okay. So, basically what we are trying to say here is that whenever you do an experiment, you need to make some reasonable assumption that whatever observations you are getting in that experiment, there must be some probability assigner function behind those observations, right? So you need to make reasonable assumptions. There could be multiple assumptions you can make, okay, about the same kind of data, but you need to make some reasonable assumptions, and those and that probability assigner function must be constrained by 3 axioms. Okay, that's the condition. Okay, so you can make any assumption which follows these 3 axioms. You can assume any probability assigner function which follows these 3 axioms. Okay, so for example, uh, another researcher in the field can claim that whatever observations you are seeing in this experiment does not come from f of theta, but they come from a process g of phi, or let us say g of lambda, okay, such that g of lambda assigns probabilities or real values to events in your event space. Okay, and this is also constrained by 3 axioms. Okay. Now, what we do in inference is that we estimate this parameter theta given the data. Similarly, we estimate this parameter lambda given the data. Okay, and let us say the parameter estimate is theta hat and lambda hat. What is this parameter estimate? This estimate is basically the value of theta with which you can generate this data from this function, and here it is the value of lambda at which this function g of lambda can generate this observed data. Okay. So, basically most likely or likely values of theta and lambda that can generate this data under these assumptions f of theta and g of lambda. Okay. So, just to explain it using an example, let us say you are tossing a coin, let us say this is your experiment, you are tossing a coin 10 times. Okay. So, if you are tossing a coin 10 times, then, and let us say we are interested in number of heads. So, what would be your sample space? If you are interested in number of heads that you would obtain when you toss a coin 10 times. So, it could be 0, either you can get 0 heads, 1, 2, 3, 4 and up to 10, right. This is, by the way, you can call it sigma x if you are thinking about a random variable that counts the number of heads in your outcome, right. So, this is these are the values of the random variables. Okay. So, when you toss a coin 10 times, these are the outcomes, these are the number of heads that you can get. Okay. Now, we need to define a probability assigner function on these values of the random variable. Okay. So, one probability assigner function that we discussed yesterday was of this form, that you can define f of x theta such that the probability for x number of heads when you toss a coin 10 times is given by this: 10 chooses x, theta to the power x, 1 minus theta to the power 10 minus x. So, this is the first probability assigner function, or the one kind of assumption you can make, that that the number of heads are coming from this underlying generative process. Okay. But you can make another assumption as well. Let us say I assume that the number of heads on a coin toss is coming from this g of x lambda such that it is lambda to the power x e to the power minus lambda divided by x factorial. Okay. So, this is just some another assumption I made, okay, where x is the number of heads, lambda is a parameter of this function, and it would indicate here the rate of obtaining a heads, okay, or the underlying on average at what rate you get heads when you toss a coin. Okay. So, this is basically another assumption I am making about the same process. Okay. Now, how reasonable is this assumption and how reasonable is this assumption? That is a different question that can sometimes depend on the theory or the kind of data you have. Okay. So, we will come back to that later. But what I am showing here is that about the same experiment, when you are tossing a coin 10 times, okay, you can basically make competing assumptions. Okay, so someone can claim that these x number of heads in 10 coin toss experiment is coming from this probability assigner function 10 cx theta to the power x 1 minus theta 10 minus x, right. Someone else can claim that this is coming from g of x lambda, right. So basically these are competing assumptions we are making about the same experiment, right. Okay. Now the goal of inference, and in fact I would say this is the final step in inference, is to um, evaluate that which assumption is better at explaining the data that you collect in this experiment. So, for example, when you really did this experiment, when you tossed a coin 10 times, you obtained 7 heads. Okay. Now, given this data, you would evaluate which assumption is better at explaining this 7 out of 10 heads when you toss a coin 10 times. Okay. Now, if f of theta is a better assumption at explaining this data, then you would say that f of theta is closer to the true generative process. Okay. But before comparing these two assumptions, you also need to estimate for what value of theta you would be able to generate this. That what is the data that you are generating 7 heads and number of coin tosses is 10. Okay. So, for what value of theta you can generate this observation from this probability assigner function f of x theta. Well, then theta should be somewhere around 0.7. Okay. So, theta can't be 0.3 for example. I mean it can be, but it is very less likely. So, more likely value of theta is around 0.7, less likely value of theta is around 0.3. Okay. So, this is called parameter estimation. So, what we are saying here is that we have already made an assumption that the data is coming from f of theta, okay. But under that assumption, what are the more likely values of theta that would have generated this data. Okay. So, that is called parameter estimation. Okay. So, similarly you will estimate parameter for the another function g of lambda as well. Okay. For g of lambda as well. So, in this function it could be the case that a value of lambda close to let us say 7 is more likely to generate this data compared to lambda equals to 1. So, let us say this is more likely. Okay. Once you have estimated these parameters, now you can compare these two generative process whether they are likely to generate this data. Okay. So, that is the workflow of inference, right. Now, so far I have not introduced anything Bayesian in this. Basically, we follow this almost same process even for frequentist analysis. So, if some of you have done courses on frequentist inference, for example, t-test, z-test or linear modeling, then you would know that what happens in a t-test, that we compare whatever you are observing. So, let us say observed t value against a null hypothesis distribution. Okay. Why is that? This is exactly the same thing that we are doing here. See, so f of theta is your alternative hypothesis, g of lambda is your null hypothesis, right. That is what we do in t-test. We compare whatever observed data you have against some null hypothesis distribution, whether that data can be generated by the null hypothesis or not. So, we are still doing, we are still comparing two sets of assumptions, competing assumptions about what could generate the observed data, right. So, basically we follow this process of statistical inference, okay. And also you calculate observed t value, which is like estimating a parameter as we are doing here, right. So, for example, you estimate population mean using sample mean. So, all that things are there as well. Anyway, now in order to practically do all this for actual data, right, in order to practically do what? Well, if you have some data that you have collected in an experiment and you assume that this data comes from a probability assigner function f of theta, right, constrained by 3 axioms. Okay. Then given the data, you will estimate what is theta hat and would try to infer what are the properties of true generative process, and you would compare it against some competing assumption as well, let us say g of phi. Okay. So, all that process requires you to properly define these probability assigner functions. So, what are exactly these functions? We have seen a couple of examples, but we will go into details of this. Okay. And this is a very critical process. Basically, this is very important for inference, because if you make wrong assumptions or unreasonable assumptions, then you are going to make wrong inference as well, right. So, it is very critical that we define, that we make reasonable assumptions about the true generative process. Okay. When our assumptions are wrong, things can go wrong. Okay. So, one example is this, that when you are doing a reaction time experiment for, let us say, a Simon task or Stroop task or any other reaction time experiment on humans, uh, the typical distribution of reaction times is something like this, that there are no reaction times beyond 30-50 milliseconds. They start around 50 milliseconds, then there is a peak, and then there is a long tail, because there are some slower reaction times, right. And that peak, the median, is around, let us say, 300 or 400 milliseconds, and they can go up to, let us say, 2000 milliseconds. So, this is the typical distribution of reaction times we get, right. Now, if you make this assumption that these reaction times come from a normal distribution with mean mu and some standard deviation sigma. What is this normal distribution, mean mu, standard deviation sigma? This is exactly a probability assigner function. The form of the function is given by a normal process. We will see what is exactly form of a normal distribution. Okay. So, this is f and it has two parameters, mu and sigma. So, this is an assumption we are making about the true generative process, that these reaction times come from a Gaussian process with parameters mu and sigma. Okay. But if this assumption is unreasonable, then you might make wrong inference sometimes. Okay. Why this assumption can be unreasonable? Well, think about it. If it is a normal distribution, nothing is stopping you to generate negative reaction times. But can you have negative reaction times in a human experiment? No. Also, a normal distribution, we will see later on all this, has the property that it has to be symmetric around the mean. But does this distribution look symmetric to you? No, it's right. It's not symmetric. It is skewed on the right hand side. Okay. So, normal distribution or this Gaussian process assumption cannot be the right assumption or cannot be a very reasonable assumption for the reaction time data. Okay. So, for example, there could be other more reasonable assumptions, like reaction times come from log normal mu sigma. So, this is another probability assigner function, let us call it z. It also has parameters mu and sigma, two parameters mu and sigma. Okay. So, it is important to make reasonable assumption, otherwise you might make some misleading inference or some inferences that would not hold if you just change the assumptions, right. So, assumptions are very critical, and of course, if you are not sure whether which set of assumptions are more reasonable, then you will of course always do model comparison, right. That is the way to go. Model comparison is critical, otherwise you cannot know which assumption is closer to the true generative process. So, there is a very famous saying by George Box, that all models are bad, but some are useful. So, we are not trying to figure out what is exactly the model or what is exactly the true generative process behind your reaction time data. We are trying to figure out that which set of assumptions are useful in describing reaction time data from an experiment, right? So, which set of assumptions are closer to the true generative process. So, that is our goal. Okay. Well, in order to do all this, now you might have gotten a sort of idea that all this requires you to understand these probability assigner functions, their properties, and what they really do, right? So, what we are going to do now is that I will introduce some basic probability assigner functions one by one, okay, and we can do a couple of exercises around them as well. Okay. So, we will start with the discrete cases, cases where the sample space is discrete. Okay. Those are called cases of discrete random variables. So, the random variables whose values are discrete. So, they would have certain kind of probability assigner functions, and continuous random variables would have a slightly different kind of probability assigner functions. Okay, we will see how. So, let us start with a very common case of discrete random variable. So, it is called a binomial random variable. Okay. And the probability assigner function associated with the binomial random variable can be called a binomial distribution. Okay. Let us see what it is. Suppose you are tossing a coin 10 times. Okay. So, I would write the trial here. Okay. Trial. This is the outcome in each ith trial. Okay. And I am defining a random variable y. I will tell you why. So, let us say this is trial 1, 2, 3, 4. So, each trial indicates one coin toss 5, 6, 7, 8, 9, 10. So, let us say in the first trial you get an outcome heads, in the second you get heads, in the third you get tails, then heads, tails, tails, heads, 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 tails, like this. Now, we need a random variable, otherwise we cannot operate on this. Okay. So, these are just head, tails, head, tails, head, tails, right. So, let us say you have a random variable which will have a value, let us call it yi, because it indicates ith trial. So, it would have a value 1 if it is a heads, it would have a value 0 if it is a tails, right. So, if it is heads, it would have a value 1, if it is tails, it would have a value 0. Okay. Like this. Good. So, this is what we have so far. Yeah. Now, all these trials hold a very important property, and the property is this, actually 3 properties. So, one is this, that they are producing binary outcome. Okay. So, they are producing either a head tails or success failure or true false, okay, that kind of outcome for which you can assign 1 0 1 0 1 0, right. So, all these trials are producing binary outcome. So, that is one property. Second, all these trials are independent of each other. What does that mean? That the coin toss in the first trial does not affect what would appear in the second trial. Okay. So, whatever outcome you are getting in the first trial, let us say first time you toss a coin you get a heads, would that affect that what you would get in the second trial? No, right. So, that is called independence property, that the trials are independent from each other. Third property is that they are identically distributed. What does that mean? It would have more, I would explain it later on in more details, but for now you can understand that, well, the coin is same, the coin is not changing, it is the same coin that you are tossing multiple times. So, the underlying process that is giving you either heads or tails, it is same. So, in each trial you are following the same underlying process, it is the identical coin. So, the probability of head is same in all these coins, and you're following the same process, you're tossing it, right? So the underlying process for each trial is identical. So all these trials are said to be identically distributed. So whenever a number of trials follow these three properties, that they have binary outcome, they are independent and identically distributed, then the summation of this random variable yi from I is equals to 1 to n, which is the number of coin tosses, follows a binomial distribution with underlying parameter theta, which is the, what is theta? Theta is the probability of obtaining heads in a ith trial. Okay. So what we are saying is that binomial distribution is about sum of this random variable yi. So sum of yi would follow a binomial distribution with probability of success theta. What do we mean by saying it follows a binomial distribution? What it means is that the probability of summation of yi, okay, comes from a function f of x theta. Okay, so we can call this random variable x. Okay, so let's say random variable x, which is summation of yi, it follows a binomial distribution. So we can say that probability of summation of yi, which is basically, if you are calling summation of yi as another random variable x, so we can do this, remember. So we can transform one space to another space using random variables, which are just functions, right? So probability of x equals to x is given by f of x theta, where, which is basically the function is this, n chooses x, theta to the power x, 1 minus theta to the power n minus x. Okay. So this is the function that assigns probabilities to number of heads, basically summation of yi. It could be anything, not just number of heads, could be anything. So this is the probability assigner function that assigns probabilities to summation of y, summation of outcome in each independent and identically distributed Bernoulli trials. So these are called Bernoulli trials. Okay, when these trials follow these three properties, okay, when a set of trials follow these three properties, they are called Bernoulli trials. And summation of Bernoulli trials, summation of outcomes from Bernoulli trials follow a binomial distribution with underlying parameter theta, which is probability of success in ith trial. Okay. And the probability assigner function associated with binomial distribution is given by this. So this is the underlying function that we are assuming is assigning probabilities to the number of successes in 10 trials, right? This thing, so we have been calling it so far probability assigner function, but it has a name, which is proper name, which is called probability mass function. So this is the name we will be using from now on for all discrete random variables. This is called PMF, probability mass function. So this is the probability mass function of a binomial distribution. Okay. All right, I will stop here. In the next lecture, we will discuss an example from binomial distribution, and then we will do some other discrete random variables like Poisson distribution. Okay. All right, thank you so much.